Hi, I'm Carly. If you're like me, you're always wondering what's out there. I didn't mean that. I meant that. And not our galaxy, other galaxies. X-shaped radio galaxies, or XRGs, are radio galaxies with really unique shapes. Normal radio galaxies have a linear structure and look like this. But X-shaped radio galaxies tend to look like this. So what we're doing is using these funky shapes to probe the black hole interactions that are going on at the center of these galaxies. At the center of an XRG is a supermassive black hole, or SMBH. Sometimes, shape can be misleading, and the X shape is just due to a deflection of material being spewed from the center of the XRG. Or, it could be the axis of a single black hole precessing or drifting. These cases are interesting, but there is a third case. Ones that are really fascinating are when two galaxies, each with their own SMBH, come closer and closer until finally the two supermassive black holes coalesce. This results in a flip of the black hole spin axes, and this flip is recorded by a change in the structure of the XRG. When we study these cases, we are learning about the low-frequency gravitational wave background. Fewer merged galaxies mean fewer black hole coalescences, which means a smaller gravitational wave background. And it's turning out that the background is smaller than expected. You may be wondering, how can we even study these things? Huge radio telescopes are in order. Collections of huge radio telescopes. The more telescopes there are, and the longer the baseline between them, the better the angular resolution of the data is. This means more fine structural details can be picked out.
Let's zoom out for a bit and look at the big picture. In February 2016, LIGO announced the first detection of gravitational waves. However, this is a different frequency range than the gravitational wave background brought about by the collision of SMBHs. The gravitational waves detected by LIGO are produced by black holes of around 30 solar masses. Supermassive black holes can be thousands of solar masses, thus producing signals of much greater amplitude. Nonetheless, LIGO has brought gravitational wave physics to center stage. Studying gravitational wave physics allows us to learn about the evolution of galaxies and determine if current evolution models are correct. How did the galaxies we see today come about? There are other consequences of gravitational wave research. LIGO, for example, forced the creation of cutting-edge lasers and vacuum systems. Gravitational wave research is further confirmation that Einstein's theory of general relativity is the right theory. We will continue to probe space and time.